1 minute ago, monitoring teams at Mount Etna detected something that made every volcanologist in Italy stop breathing. A fresh fracture nearly 30 meters long has split open across the volcano's southeastern flank, cutting through ancient rock like a knife through butter. The line runs parallel to the scar left by a collapse 8,000 years ago, a collapse that unleashed a tsunami tall enough to drown a 10-story building. What if this is not just another crack? What if the entire flank is preparing to slide into the Mediterranean? And if 500,000 people live on ground that could vanish in minutes, why can't anyone stop it? Before we dive into the answers, don't forget to like the video and subscribe to the channel, and let us know in the comments where you're watching from. The drone footage came in at 0430 UTC. A thermal imaging sweep along the Valley del Brobo revealed the rupture extending from 2,400 meters elevation down to 900 meters, carving through layers of compacted ash and basalt that have stood for millennia. The fracture measures 30 meters in length, up to 2 meters wide in places, and shows fresh displacement of at least 15 centimeters on the downslope side. What alarmed the monitoring team at Italy's National Institute of Geophysics and Volcanology was not just the size, but the location. The crack follows the exact boundary of the ancient collapse zone. An INGV geologist stationed at the PC Denner Observatory called it a nightmare scenario. The fracture sits atop a known slip plain, a layer of weakness buried beneath the mountain's eastern face. For years, scientists have tracked slow seaward movement of Etna's flank at 3 to 5 centimeters annually, dismissing it as gradual spreading. But this rupture appeared overnight, with no warning tremors, no magma intrusion, no volcanic gases surging to the surface, just a clean break in the mountain's skin. Within 3 hours of the discovery, Italian civil protection authorities closed the upper slopes.
Red exclusion perimeters now circled the fracture zone, blocking access to hiking trails, mountain refuges, and the cable car station at 2,500 meters. Airspace restrictions extend 5 kilometers around the summit, grounding tourist flights and forcing scientific helicopters to file special clearances. LAR-equipped drones have been deployed on rotating shifts, scanning the fracture every 2 hours to detect any widening or propagation. Ground-based laser rangefinders now bracket the rupture from observation posts on both sides. Field teams rappelled into the fracture within hours, installing crack meters across the gap at 3 separate depths. Each device measures displacement to the nearest millimeter, transmitting data every 10 minutes via satellite link. Additional GPS stations have been bolted to stable bedrock flanking the rupture, creating a network that can detect lateral motion as small as 5 millimeters. At INGV headquarters in Catania, screens display live feeds from 8 cameras trained on the fracture zone, their infrared sensors hunting for temperature anomalies that might signal rising magma or escaping gas. But the instruments are finding something else entirely. INSAR satellite data from the European Space Agency shows ground displacement radiating outward from the fracture. Between November 15th and November 26th, the downslope side of the crack moved 4 centimeters seaward, while the upslope side remained stationary. The pattern is unmistakable. This is not volcanic inflation pushing the mountain apart from within. This is gravity pulling a massive slab of rock toward the ocean. GPS stations along the coast, 12 kilometers from the fracture, recorded synchronous eastward shifts of 2 centimeters during the same period. The movement is coherent across the entire southeastern flank. Crack meter data from the rupture itself shows stepwise opening. The fracture widened 8 millimeters on November 19th, another 6 millimeters on November 23rd, and 4 millimeters on November 25th. Each increment occurred without seismic activity, without tremor, without any of the usual volcanic precursors. Photogrammetry teams have built 3D models of the fracture using drone-captured images, overlaying them with historical topographic data from 2019. The comparison reveals that the rupture sits directly atop a buried fault plain, the same structure that ruptured 8,000 years ago when Etna's eastern flank collapsed into the Ionian Sea. Every data point confirms the same terrifying conclusion: the ancient slip plane is reactivating. Field samples retrieved from the fracture walls tell a deeper story. Core drilling along the rupture has exposed a layer of material unlike anything in the surrounding rock. This gouged layer, sandwiched between solid basalt above and fractured sediment below, is composed of clay-rich material with a consistency closer to wet sand than volcanic stone. Laboratory tests at INGV show the gouge has a shear strength less than 1/1000th that of intact basalt. Under stress, this layer behaves like a lubricant, allowing the massive flank above to slide with minimal resistance. The mountain is sitting on a slippery foundation. Gas sampling at the fracture has revealed elevated concentrations of carbon dioxide and hydrogen sulfide, both rising from depth along the rupture plane. CO2 levels measured 18,000 parts per million near the fracture floor, 3 times background levels on the surrounding slopes. These gases are not coming from shallow magma chambers beneath the summit craters. They are seeping upward through fractures in the slip plane, driven by tectonic stresses compressing the base of the flank. The volcano's internal plumbing is being disrupted from below. Thermal imaging of the fracture reveals localized hotspots where temperatures reach 62 degrees Celsius, far above the ambient surface temperature of 18 degrees. These anomalies cluster at the base of the rupture, where the slip plane intersects the modern fracture. Heat is not rising from the summit magma system. It is being generated by friction along the moving fault plane, a sign that the flank is already in motion, grinding against its foundation as it inches toward the ocean. What came next shocked even the scientists. The mechanics of a flank collapse are deceptively simple. A volcanic edifice like Etna is not a solid monolith, but a pile of layered material. Lava flows, ash deposits, pyroclastic debris stacked over hundreds of thousands of years.
When this pile sits on a weak base, gravity becomes the dominant force. The southeastern flank of Etna is estimated to weigh 25 cubic kilometers of rock, roughly 70 billion tons. This mass is perched on a foundation that dips 15 degrees toward the ocean, steepening offshore to 25 degrees beneath the seafloor. The flank is an inclined slab sitting on a tilted ramp. Add the weight of new eruptions constantly piling material onto the summit, and the pressure on the slip plane increases relentlessly. Magma intrusions can destabilize the system further. But recent research reveals that gravity, not magma, drives the movement. C4 geodetic instruments deployed between 2016 and 2017 recorded a 4-centimeter slip event along the offshore extension of the fault during an 8-day period in May 2017. The slip occurred without any associated earthquakes, without summit eruptions, without magma rising through the volcanic conduits. The flank moved because gravity pulled it. This finding upended decades of assumptions. Scientists had believed that magma pressure was the primary driver of flank instability at Etna, that the mountain only moved when volcanic forces pushed from within. But the seafloor data, combined with onshore GPS measurements, showed the opposite. Movement is greatest at the coast and decreases toward the summit. If magma were driving the motion, the pattern would reverse, with maximum displacement near the volcanic center. Instead, the data shows a system in gravitational collapse, its underwater base sliding seaward and dragging the entire flank with it. The signs were already spreading. Computer simulations of a catastrophic flank collapse at Etna paint a grim picture for the Mediterranean.
If 25 cubic kilometers of rock were to slide into the Ionian Sea at velocities approaching 200 kilometers per hour, the resulting displacement would generate tsunami waves with initial heights between 20 and 25 meters. Wave propagation models developed by INGV researchers show these tsunamis reaching the coast of Calabria within 30 minutes, crossing to Greece in 90 minutes, and striking North African shores in 2 to 3 hours. The entire eastern Mediterranean would be in the impact zone. These are not hypothetical numbers. They are derived from modeling the 8,000-year-old collapse event constrained by geological evidence of that ancient disaster. Submarine surveys have mapped debris fields extending 20 kilometers offshore from Sicily. Massive blocks of Etna basalt, jumbled with marine sediments, all dated to approximately 8,000 years before present. Sediment cores retrieved from the floor of the Ionian Sea show chaotic deposits, layers of displaced mud and sand that can only form when a tsunami stirs the seafloor. The Mediterranean has seen this catastrophe before. Tsunami deposits have been identified across the region. In southern Italy, gravel layers containing Etna ash sit atop Bronze Age settlements, evidence of waves powerful enough to transport cobbles kilometers inland. On Malta, sediment cores from coastal lagoons show abrupt changes in salinity and sediment type around 8,000 years ago, consistent with seawater inundation from a large tsunami.
In Greece, coastal deposits of similar age contain reworked volcanic material with a chemical signature matching Etna basalt. And then there is Atlet Yam. This Neolithic village on the coast of present-day Israel was abandoned suddenly around 8,000 years ago. When archaeologists excavated the submerged ruins in the 1980s, they found evidence of a rapid departure. Fish had been gutted and sorted, but left to rot. Stone tools lay scattered in workshops. Grain storage pits were half empty, suggesting the inhabitants fled before completing their harvest. Radiocarbon dates from the site align precisely with the age of Etna's offshore debris field. Researchers now believe the village was destroyed by the tsunami from Etna's collapse. Waves traveling 1,800 kilometers across the Mediterranean to strike the Levantine coast. The ancient disaster was not a myth, but the ground had one more secret. Italian civil protection agencies have developed evacuation plans for volcanic emergencies at Etna, but these plans were designed for lava flows and ashfall, not catastrophic flank collapse. The logistics of moving 500,000 people from the red zone, the densely populated area directly atop the unstable flank, would overwhelm regional infrastructure. Catania, Sicily's second-largest city, with a population of 310,000, sits less than 30 kilometers from the coast where tsunami waves would strike first. The city has 2 evacuation routes inland, both 2-lane highways that bottleneck at mountain passes. During a 2019 emergency drill, simulated evacuation of Catania took 14 hours under ideal conditions. In a real collapse, there would be no ideal conditions. Earthquake swarms accompanying the initial flank failure would damage roads and bridges. Panic would clog highways with abandoned vehicles. Coastal residents trying to flee inland would collide with mountain residents trying to reach higher ground. Communication networks would overload within minutes as hundreds of thousands tried to call for help simultaneously. Emergency responders interviewed during preparedness exercises admitted privately that if the flank went, they would be in survival mode themselves, not coordinating rescues. The infrastructure cannot handle a real collapse. Maritime evacuation is no solution. Catania's port can accommodate perhaps 20,000 people on ferries and commercial vessels if given days of advance notice. During an unfolding collapse, port facilities would be among the first infrastructure to fail. Tsunami waves would arrive within 30 minutes of the initial slide, far faster than ships could be loaded and moved to safe waters. Coastal fishing villages along the Ionian coast have no tsunami warning sirens, no elevated evacuation zones, no designated assembly points for maritime rescue.
Historical monitoring data reveals just how precarious the situation has become. PPS measurements show the flank has moved 1.2 meters seaward since continuous monitoring began in 1981.
That is an average rate of 2.8 centimeters per year. But the motion is not steady. It accelerates during periods of volcanic activity and continues even when the summit craters are quiet. C4 instruments have documented slip events lasting days to weeks, during which the flank moves several centimeters without producing felt earthquakes. The mountain is sliding silently. At Refugio Sapienza, a mountain refuge at 1,900 meters elevation, manager Giuseppe Torresi has watched the volcano's moods for 30 years. His family has operated the lodge since 1956, serving hikers, skiers, and tourists who come to witness Etna's spectacular eruptions. But the new fracture has changed everything. "We heard a sound like thunder on the night of November 18th, he said, standing near the closed cable car station. Not an explosion, not a rockfall, just a deep rumble that seemed to come from inside the mountain. The next morning, guides found the crack. Now we are told to prepare for possible permanent evacuation." Mount Etna holds one of the longest documented records of volcanic activity on Earth, with written accounts stretching back to 1500 BCE. Ancient Greek historians described eruptions that darkened the skies and sent lava rivers to the sea. Roman scholars recorded ashfall in North Africa from Etna's explosive phases. Over the past 500,000 years, the volcano has built and rebuilt itself dozens of times, each major eruption adding layers to its edifice. The current structure, the Mongebellu stratovolcano, began forming 15,000 years ago. Since the year 1600, Etna has produced at least 60 flank eruptions and hundreds of summit eruptions. Nearly half occurred in the 20th century alone. Between 2000 and 2024, the volcano has erupted almost continuously, with flank fissures opening in 2001, 2002, 2004, and 2008, and summit activity recorded nearly every year. The 2024 eruptive sequence at Verigine crater lasted from June through August, producing 6 major lava fountaining episodes and filling adjacent craters with fresh magma. Etna erupts more frequently than any volcano in Europe. This constant activity reshapes the summit faster than topographers can update their maps. In 2021, the southeastern crater reached a height of 3,357 meters. By September 2024, after summer eruptions filled Verigine crater with lava, the summit had arisen to 3,043 meters. Layers of basalt, scoria, and volcanic ash now blanket the eastern flank to depths exceeding 300 meters. Each eruption adds weight to an already unstable slope, increasing the gravitational stress on the slip plane below. The volcano is building its own instability. Yet the latest eruptions have produced something unexpected. Lava samples collected from the August 2024 events contain mineral compositions that do not match Etna's historical basalt signature. Petrographic analysis reveals crystals of pyroxene and olivine with unusual zoning patterns, suggesting rapid changes in magma chemistry at depth. Whole rock geochemistry shows silica content 3% higher than typical Etna basalt, edging toward an andesitic composition. Laboratories in Rome cannot classify the material within existing volcanic rock categories. The lava's behavior during eruption was equally unusual. Instead of forming the typical pahoho or flows characteristic of basaltic eruptions, the August lava produced short, stubby flows with surfaces resembling block lava, a feature more common in higher viscosity magmas. Pyroclastic flows, rare at Etna, occurred twice during the summer sequence, sending superheated avalanches of ash and rock down the southeastern flank. Seismic data from the eruption period shows deep tremor sources at 15 to 25 kilometers depth, far below Etna's main magma storage zone at 3 to 6 kilometers. The volcano's internal plumbing system may be fundamentally changing. If deeper magma chambers are becoming active, or if Etna is tapping a more evolved magma source, the implications for flank stability are profound. Changes in magma composition can alter gas content, increasing explosive potential. More viscous magmas can clog conduits, building pressure that could trigger catastrophic eruptions. And if deep structural changes are underway, the stress regime affecting the slip plane could shift unpredictably. Scientists watching the data cannot predict what happens next. This was only the first warning. As of November 27, 2025, the southeastern flank of Mount Etna continues moving seaward at rates now exceeding 7 centimeters per year, the fastest movement ever recorded by continuous monitoring. The fresh fracture discovered on November 18th has widened by a cumulative 31 millimeters with no sign of stabilization. INSAR data confirms that the area affected by coherent deformation now extends across 180 square kilometers, encompassing not just the visible rupture, but a vast subsurface fault plain that reaches beneath the seafloor. Evacuation systems designed for volcanic eruptions are inadequate for the scale of disaster a flank collapse would create. Tsunami warning systems in the Mediterranean remain fragmented, with no unified protocol for rapid alert dissemination across national boundaries. Coastal infrastructure from Sicily to Greece to North Africa was built without consideration of tsunami risk, leaving millions vulnerable. Scientists know the flank is moving. They know it sits on a weak foundation. They know gravity is pulling it toward the sea. They know an 8,000-year-ago collapse devastated the entire Mediterranean basin. What they do not know is when or even if the next collapse will occur. The transition from slow creep to catastrophic failure could happen in hours, or it might never happen at all. Current monitoring can detect changes, but cannot predict the tipping point. Computer models can simulate the disaster, but cannot forecast the trigger. If the flank gave way tonight while Katana sleeps and ferries are docked and emergency responders are off duty, could 500,000 people reach safety before the waves arrived?